Yesterday we learned about triangles. Today we are going to extend this up to talk about what are called polygons. A polygon is defined as having many angles. So poly as a prefix means many. What other words can you think of that start with poly?
Polyester.
Okay. Polyester means that there are many different kinds of fibers that are making that material, that it's a mix of a lot of different types of fibers.
Polytheism.
Polytheism means you believe in many gods. Polygamy means what? Many wives. So when we have poly at the beginning of a word, that as a prefix means many. So polygon means that it has many angles or many sides. There are some restrictions of how this works. First, it has to be made of coplanar segments so that a polygon is a flat figure. Right? If it's in a plane, it is not a three-dimensional solid. It is a flat planar figure. Then it says also every segment intersects exactly two other segments, one at each endpoint. So that kind of tells us a couple things, that this shape can't be totally open. It has to be closed off. And the segments can't cross each other. Okay. And then the third restriction there says that no two segments with a common endpoint are collinear. So that means every time that you hit one of those endpoints, which will be called vertices, just like they were in triangles, we have to have at least a slight turn. It can't keep going on a straight line. It has to at least take a little bit of a turn every time we hit a vertex or a corner. A convex polygon says that it's a polygon so that no line containing a side of the polygon contains a point in the interior. It's a little bit hard to understand what a convex polygon is just by reading that, so I like to think of it in terms of its opposite, which is called concave. We're not going to be working with concave polygons, so that's why it's not defined here. But when we see what concave is, it's easier to understand what convex is. A concave polygon is a polygon that bends in inside of itself. Okay. We will not be working with concave polygons. So all of ours should not fold inside of themselves like this one does. The way I remember this is called concave is because I get a little cave where animals can live when a figure bends inside of itself, and you shouldn't have anywhere like that in the ones that we're working with. Okay, so they shouldn't be taking any indentions. So a convex doesn't have any indentions. Then we've got the names of a lot of special polygons here. So we talked about triangles yesterday. Triangle, tri as a prefix means 3. Quad as a prefix means 4, so quadrilateral is 4. Penta means 5, like the Pentagon in Washington, D.C. has 5 sides to it. Hexa as a prefix means 6. For some reason, the book did not think 7 was important, so they skipped that one. I don't know why, but I skipped it too then. But just FYI, 7 is called a septagon. Sept, S-E-P-T, septagon. 8 is an octagon. Octa means 8, like an octopus has 8 legs. A decagon, so they skipped 9 too. 9 is called a nonagon. Again, I don't know why they decided to skip that one. I think nonagon's a really cool word, but they skipped that one. 10 is a decagon, like decade is 10 years. Deca means 10. Then after that, they said, we'll just call them ends. So you can have any number of sides. So we could have like a 15-gon, or a 42-gon, or a 100-gon, which would really be called a centagon. Centa, like century, is 100. I mean, some of them do have cool names, like centagon, or 12 is a dodecagon. But after 10, we're just going to start calling them by the number of sides they have gone.
Can we just do that?
No, you need to know these names of these. That will be something that could be tested on the quiz on this next week, is knowing these special names. A diagonal is a segment that joins two non-consecutive vertices, because the consecutive ones would already be connected. And so a diagonal is a segment that joins two of the vertices that are not already connected. And it'll go through the figure then. So we have 2 theorems that talk to us about the angles of a polygon. The first one says the sum of the measures, so if we add up all of the angles of a convex polygon with n sides, is and then minus blank, but hopefully yours is there, n minus 2 times 180, if it's not there right there. I'm not going to prove this, but I will show you why it is what it is. So let's say I start with a pentagon, so 5 sides, and I draw in all of the diagonals from one of the points. So if I pick this point and I draw in all the diagonals, I could draw a diagonal here and a diagonal here. When I did that, it cut up this pentagon into 3 triangles. How much is inside of a triangle?
180.
180. So each of these triangles should have 180 inside of it, and so this pentagon should have 3 times 180 inside of it. Well, it started out as a 5, and then it became a 3, so it looks like we subtracted 2, but maybe that was just something lucky that happened here. So what about if I would take a 6-sided, a hexagon? Take one point, and draw in all the possible diagonals, and I ended up with 4 of them. So I started with 6, I ended up with 4, so it looks like I subtracted 2 again. And that's not a proof, but just a couple of examples that show why this formula works the way that it does. If I draw in all the diagonals from one point, I will end up with 2 less triangles than the total number of points. And so I can multiply the number of points, n, subtract 2 from that would tell us how many triangles we have, times 180 for each triangle. The sum of the measures of the exterior angles, theorem 14 says, is 360. Always. No matter what kind of a figure it is, if it's convex, the outside angles will add up to 360. Okay. A regular polygon says that it's one that is both equilateral. What does equilateral mean?
The segments are equal length.
The sides are of equal length. And equiangular. What does that mean?
The angle.
The angles are of equal size. So in regular polygons, the sides are the same length and the angles are the same size. And so that's going to be important to us in solving some of our problems. So our first problem says a polygon has 102 sides. So we don't have a special name on this one. It's just 102 gon is what we would call this one. It's probably like a docentagon or something. I don't know. But we don't have a special name for it. We want to know the interior angle sum. That first theorem told us that the angles inside should always be n minus 2 times 180 for any convex figure. And we will only be working with convex figures. N is the number of sides that it has. So that would be 100 and 2. Which is 100 times 180. Or 18,000 degrees inside of the angles of that polygon.
Wow, that's a lot of degrees.
That is a lot of degrees inside of the angles of that polygon.
Separation.
The exterior angle sum is what?
360.
360. Always. No matter what. No matter how many sides and angles it has, 360 for the outside.
What is the outside?
We talked about exterior angles yesterday as being like extending out one of the sides.
Okay.
So if we did that at each corner
All those added together.
and extended those out, that will always be 360 for any figure. For the next one, we have a chart, and we're told that these are for regular polygons. That means every inside angle should be the same size, and also every outside angle should be the same size. So it wants us to find the measure of each interior and exterior, not the total sum, but we will use those formulas here. So the total exterior should be 360. So if there are 6 sides, there are also 6 angles. So how much will each of the outside angles be? 60. 360 for the whole thing, divided up by 6, since there's 6 of them. So for the exterior, we're going to take the total 360 and divide it up by how many we have, and that'll tell us how many each of them will be. Our interior rule is n minus 2 times 180. So for this one, I would do 4 times 180 gives me my total inside. And that is 720. So then how do I figure out how big each of them is? Divide it by 6. And that gives 120. Okay, so we can find out our total inside using that n minus 2 times 180 formula. And then we want to divide it up by how many we have. And that'll give us how big each inside one is. So for the next column, if I have 10 sides and 10 angles, and the whole outside is supposed to be 360, how big is each of those 10? 36. We can divide it up evenly since it's regular. They're all the same size. And so if I have 10 36-degree angles, that would add up to the 360 that I need. For the interior, we need to do n minus 2, so that's 8 times 180. And that is 1,440. That's the total inside. So how do I figure out how big one of the insides is? Divided by 10, since there's 10 of them. So that gives me 144. I'm going to skip that next column for a minute and jump on over to where 10 is given as an exterior. So if 10 is given as an exterior angle, and all together we're supposed to have 360, how many 10-degree angles does it take to make 360 degrees? 36. So there must be 36 sides and angles on that thing. So for that, we're still just dividing. Okay? So for either of those first two, if you're given one of them, we just divide it out from the 360. Then to find our inside, I would subtract 2 from that and get 34 times the 180. And I have no idea what that is, and I didn't write it down. 34 times 180.
It's like
6120. And then how do I figure out how big a single interior is? Divide that by 36, and I get 170. I want you to now do the two columns where there is a 20 in it. Save the last two. We will talk about those together. So I'm just going to give you a moment to look at the two columns where you were given 20s and figure out the answers on those, and then we will discuss them. So if I have 20 sides and angles, and the whole outside is supposed to be 360, how big is each of the outsides? 18. Do 360 divided by 20, and that gives 18 for each of the outsides. For the insides, I would take the 20 sides that we have and subtract 2, that gives me 18 times 180. And I would get that and divide it out by 20 to figure out how big each of those interiors is, and that gives me 162. For the other column with a 20 in it, if each outside is 20 and the whole outside is supposed to be 360, then how many of them are there? 18. It's still the same division, it's just the other way. So now for the last one, I'm going to do 16, the number of sides minus 2, times 180. That would give me the whole inside. And then I would want to divide that out by 18, and that gives me 160. For the last two, we could work with what we're given here and solve back using that n minus 2 times 180 formula for the number of sides. The algebra gets a little bit messy, so there's an easier way. Find a pattern that relates the exterior angle to the interior angle. What is always true about an exterior angle and its interior angle? They add up to 180. every single time the exterior angle and the interior angle add up to 180. So we can see a picture for why that would be. If I take and draw out an exterior angle here, it has an interior angle that's right next to it, and they make a straight line. So an exterior angle and an interior angle should always add up to 180. So 60 and 120 is 180. 36 and 144 is 180. 18 and 162 is 180. 10 and 170. 20 and 160, always 180. So if the interior is 179, how big is the exterior? 1. How many 1 degree angles does it take to make up the 360 that we need? 360. So that figure has 360 sides.
Like a circle.
It is going to look really close to a circle if you would try to draw it. It's not quite technically a circle, but it's going to look really close to one. If each inside is 90, how much is left for the outside? 90. Because an inside and an outside should make a straight line. How many 90s does it take to make up the 360 that we need? 4. There will be a chart like this in your homework, and there will be problems like this on your quiz. I don't think they're set up in chart form, but where it's asking the same kind of things to find interiors and exteriors or sides for a regular polygon. Okay. Questions?
Do the last column.
Yep, hold on just 1 second. So this is assignment 1 to 6, 8 to 10, and then 12 to 15 for tomorrow.